Problem 37 reads, members of the fire department lean a 26-foot ladder against the building. The side of the building is perpendicular to the level ground so that the base of the ladder is 10 feet away from the base of the building. To the nearest foot, how far up the building does the ladder reach? So let's do a little diagram here. So we have a building. Now we have the ground level floor. And it says members of the fire department lean a 26-foot ladder against the building. So when they talk about the side of the building is perpendicular to the level ground, it means that this is a 90-degree angle, which is what we need to have in order to solve this problem. Otherwise, we would need to do something else. So that's an important piece of information. And then it says that the ladder measures 26 feet, so we can draw this as a ladder. And it measures 26 feet. And finally, they say that the ladder is 10 feet away from the base of the building. So that's this distance here. This is equal to 10 feet. Now everything is in feet, we don't need to convert, and essentially they want us to know to the nearest foot how far up the building the ladder reaches. In other words, we need to know this measurement, x. So to solve this, simple, we use the Pythagorean theorem. Remember, when you have any right triangle like this one, the sum of the sides squared, in other words, a squared plus b squared, will always be equal to the hypotenuse squared. In this case, we know one of the sides, so that's the 10 feet right here, so 10 squared plus, now we don't know the other side, so we'll put that as x squared. Now, the sum of these squares should be equal to the square of the hypotenuse, which we know measures 26, so 26 squared. At this point, all we need to do is be able to solve this simple equation. 10 squared is, of course, 100, so we end up with 100 plus x squared is equal to, now 26 squared is equal to 676, so that's our next step. Now we want to solve for x squared, so we subtract 100 from both sides. That leads to x squared, because these hundreds cancel. X squared is equal to 676 minus 100, which is 576. Now we know, given this expression, the measurement of x squared, but we want to know the measurement of x. So we have to take the square root of both sides, because the square root is the opposite of raising to the second power. So these will cancel, giving us x. Strictly speaking, we would end up with both a positive and a negative answer, but we're only interested in the positive answer in this case. So the square root of 576 is equal to 24. So the side measures 24 feet, which is choice E. Now, be careful because it says to the nearest foot, how far up the building does the ladder reach? And those of you that are very, very careful in reading these prompts could be thrown off by that statement, to the nearest foot. You realize that you get a nice integer here, and you may be thinking, did I do something wrong? Because it asks to the nearest foot, maybe I did something incorrectly, but no. In this case, the answer is a nice integer, whole number. And so there's no need to trunk. For problem 37, with a ladder, we know that it's 26 feet, the hypotenuse, and 10 feet, one of the sides. So using the Pythagorean theorem, we would do 10 squared, so that's 100, but then we would do 26 squared, the hypotenuse, minus that 100. So that gives us 576. But the square of this is the measurement of the side, which in this case would correspond to the height of the building that they're going to be able to get to with this ladder. So we do second x squared, which is accessing that root symbol, so that's the square root symbol of the answer, or of 576, whatever, and you're going to get 24, which is the correct answer. For problem 38, it reads, a square is circumscribed about a circle of a 5-foot radius as shown below. What is the area of the square in square feet? This is a very simple prompt. Just be careful that you don't make a mistake that a lot of students will make on this one. So if the circle is circumscribed, means that the sides, the edges of the circle will match perfectly the sides of the square. So what that tells us is that if we're able to know the diameter of the circle, we'll know the measurement of the side of the square. Well, if they give us a radius and the radius is 5, just know that twice the radius is equal to the diameter. In other words, another segment measuring 5 will give us a side measurement of 10 feet. So yes, the diameter is 10 feet, and in this case, so is the side of the square. Notice that pi is nowhere to be seen here. Pi is used for circles when you find areas and things like that, but when you're talking about the radius, and in this case it's defined just as being 5 feet, well, the diameter is twice that, which is 10 feet. That's it, simple as that. Now, if you know that a square measures 10 by 10, because if it's a square, then all sides are equal, of course. You know how to figure out the area of a square. You simply multiply the sides. Area of the square is equal to 10 times 10, which is equal to 100 feet. Choice G. So H is incorrect because it has a pi symbol. Don't be thrown off by that. And then the other ones are wrong because obviously the math doesn't add up. For problem 38, all you had to do was, knowing that the diameter is 10, that is equal to one of the sides, so 10 squared is 100, or you simply multiply 10, the base, times 10, one of the other height of the rectangle, and of course you get 100. For problem 39, reads, the ratio of the side lengths for a triangle is exactly 7, 11, 13. In a second triangle similar to the first, and that's key here, the shortest side is 9 inches long. To the nearest tenth of an inch, what is the length of the longest side of the second triangle? So to do this, you can visually see what's happening. If we draw just a triangle, we'll make this a 7 by, say, 11. Then the long side by 13. That's what this is telling us. It's 7 by 11 by 13. Now, a second triangle is similar, and the use of the word similar here means that they're proportional. In other words, that when you have the second triangle and the shorter side measures 9 inches long, then all of the other measurements are going to be proportional to this first triangle. This is the first one, this is the second one. So if this is 11, this is some unknown value, and this, the longest side 13, for this other second triangle will be equal to x, the value that we want to solve for, because they're asking us for the length of the longest side of that second triangle, which is this one. So we really don't care about this measurement at all, and we don't need it. Now, because this is a ratio problem, a proportionality problem, what we can do is the following. We can say, from the first triangle, 13 is to 7, as, I use the equal sign here to create my equation, x, the longest side of that second triangle, is to its short side, which is 9. Notice how if the long side of the first triangle is here in the numerator, I'm going to make sure that the long side of that second triangle is in the numerator as well, the x. And then if the short side, the first triangle is the denominator here, the 7, then I'll make sure to have the short side of that second triangle in the denominator as well. Now I need to solve for x. Very simple. I have on the right side, I have the 9 dividing the x, so I can send it to the other side multiplying. So I end up with the equation 9 times 13 divided by 7 is equal to x. That's the long side I'm after for that second triangle. Now, to multiply a non-fraction times a fraction, very simple. You simply put a 1 under the non-fraction. So now you're multiplying two fractions. Multiplying two fractions is very simple. You multiply numerators straight across. So 9 times 13, and then divided by, multiply the denominators straight across, 1 times 7, which is 7. So this will be the value of x, the value we're after. So if we multiply 9 times 13, we get a value of 117. And 117 divided by 7 will be the value of x, that side we're after. So we find, using your TI, that x is equal to 16.714, etc. Now they want us to the nearest tenth of an inch, so we need to round. So to the nearest tenth of an inch is to this decimal right here. The one to the right is a 1, so whenever it's 4 or less, you keep The one you're rounding to, you keep it the same. You don't round up. So x is equal to 16.7, in this case, inches. So inches long. Problem 39, one of the equations that you may have obtained was x is equal to 9 times 13 divided by 7. So you could do that by keying in 9 times parentheses 13 divided by 7. Notice that I didn't have to use the fraction form there. And you got 16.714, etc., which rounds to 16.7. The other choice was to actually use a fraction. You can do that 9 times, and then you go to math, you go to frac for fraction, 1, the numerator, denominator, and then there you enter 13, scroll down, 7, forward, and you get an answer. The problem is that it's now in fraction form, and if you want to change that, you would either key in 117 divided by 7, 16.714, etc., or you would have to use one of the math keys again, but this would be easier. But you can see that in this case, it's actually the first choice that's ideal here. For problem 40, it reads, in the figure below, ABCD is a trapezoid. E lies on line AB, and angle measures are as marked. What is the measure of angle CDB? So they want us to come up with this angle right here. You have to be very careful on these because you cannot use your eyesight to figure out angles. Never do that. You must use some property of geometry, of triangles, of trapezoids, of whatever, to figure this out. You cannot assume, say, that the angle we're after, well, it looks kind of the same as this angle right here, so the answer should be F, 25 degrees. That's absolutely incorrect. So make sure you don't fall into that trap. So how do we solve this? Well, the trick is to do the following. First of all, for the trapezoid, trapezoids can have all sorts of crazy shapes. For example, this could be a trapezoid. And you can see that this angle, this angle, this angle, and this angle are all different. So you cannot assume, just because it's a trapezoid, that the bottom angles are going to be the same and that the top angles are going to be the same. So what do we do in this case? Well, let me just focus on the trapezoid. So I'm going to draw the trapezoid down here. It's just a sketch. I'm not focusing on this line right now, okay? So the trapezoid given by points A, B, C, and D, what do I know? I know that this angle measures 80 degrees. Then, focusing on this part right here, I know E lies on that AB segment, so that's important. I know that this measures 100 degrees. Well, if this measures 100 degrees, then I know what this angle measures. Because remember, if you have a straight line, this angle will always be equal to 180 degrees in a Euclidean geometry, in a flat surface, which is what we're working with here. So, if this entire angle is 180 degrees and this measures 100, now I know that the difference is this one. So 180 minus 100 is equal to 80 degrees. This is crucial because now I know for a fact that I have a trapezoid that is perfectly symmetrical because these two angles are the same. In other words, these two angles, let's call them x, will be the same. That's why I can use the same variable for them. Why? Because this is a symmetrical trapezoid. Now, the next step is to figure out what this angle right here, in other words, this one is equal to. How do I do that? Well, remember that the sum of all interior angles, so angle 1, angle 2, angle 3, and angle 4 of a four-sided shape, the sum will always be equal to 360 degrees. So how many degrees do I have so far? Well, 80 plus 80 is 160. So let's subtract from 360, 160. That gives us a total of 200 degrees. Now, because these two angles are the same, you need to divide 200 by 2, which gives you 100 degrees. That is the value of x. In other words, that's the value of each of these angles. So let me redraw this so that we can have a clean trapezoid here. And this is point E. We know this is 80, We know this is 80. We now know that this is 100, and we now know that this is 100. And that was critical because now when we go back to our shape here, because we want to know angle CDB right here, this angle, this shape, which is a triangle, has the following angles. The given angle of 25 degrees, the angle we found here of 100 degrees, that comes from the trapezoid, this one. That one corresponds to angle BCD. It's the same as this one. And now we know that this is the angle CDB that we want to figure out. So what is angle CDB? Well, very simple. The sum of all interior angles of a triangle, doesn't matter what kind of triangle you have, will always be equal to 180 degrees. How many do I have so far? Well, I have 100 plus 25. So I have 125 degrees so far. So if I subtract from 180, 125, I get a total of 55 degrees, the measurement of the angle we were trying to determine. For problem 40, we could simply do 180 minus 100. That gives us the angle of the trapezoid. So knowing that it's 80 and 80, we now have a perfectly symmetrical trapezoid. And so it opens up the door to find the angle of the top of the trapezoid. Knowing that 80 plus 80 is equal to 160, we do 360 minus 160, which gives us 200. So we have 200 degrees between two angles, the B and C. So if we divide that by 2, we get 100 for each. So now we have a triangle with 125 and then the angle we're looking for. So we know that the interior sum of the angles of a triangle is 180. So subtract 100, the one we found, and the given of 25, and you get 55, which is the value of the angle we're looking for. In other words, H.